Hello everybody, I am Dr. Muhammad Hayat Razvi. I welcome you back to my radar systems class. Now let us discuss second chapter of radar systems, which is CWN frequency modulated radar. CW stands for continuous wave radar and FM is frequency modulated radar. If you observe the syllabus, the first topic is Doppler effect followed by CW radar block diagram. Let us now jump into the actual topic without wasting much time. The main function of CW radar is to detect the objects and to measure the velocity of the moving objects. These two functionalities are the main functions of the CW radar. The sine wave, CW means continuous wave. The continuous carrier wave that is transmitted by the radar goes, hits the target and comes back in the form of echo. If there is an echo, then the radar understands there is a target. If there is no echo, then it understands there is no target. The incident signal will be pumped into the space environment to an infinite distance. So, echo represents the presence of the object. And if the echo signal carrying the same frequency which whatever that is transmitted, then the radar understands the target is stationary target. That is, it is not moving. If there is a shift in the frequency, either the shift may be positive or negative, depending upon the polarity of the frequency, the radar system understands whether the target is approaching or receding. In the previous case, in the first chapter, it was pulse radar which we have studied. In pulse radar, the transmitter knows the time instant or the time mark when the pulse has left the antenna, left the transmitter system. And similarly, it knows the time at what time the echo has came. Now, the gap between the transmission of the pulse and the reception of the echo, there will be a time lapse. Depending upon the time, we know the velocity of light, all the electromagnetic waves travel with the velocity of light. So, the electromagnetic wave that has left the transmitter at a particular instant t and returned back to the receiver at t plus delta time. Now, this delta time is the time required to go to the target and come back to the receiver. So, if you divide it by 2, then you can understand at what distance the target is. That is called as radar range. That facility is not available with the CW radar because there is no time mark in the CW radar. A continuous wave, consider a sine wave with high frequency like F0, is continuously transmitted from the CW radar, so you cannot have a time mark. That is the reason why CW radar cannot measure the distance of the object. So, the next point is the CW radar it can be monostatic or bistatic. That means if the radar system may be stationary and the target may also be stationary, that is called as bistatic. If the target is approaching us, consider we are standing in an air traffic control room and the flight is approaching us. This case is called as monostatic case. Or else, if the radar is airborne radar, which we are operating from a flight, and we are trying to measure the distance between the ground station or from a mountain. Now, this is also the case of monostatic. Either the transmitter or the target should be in moving condition, then it is called as monostatic. If both are moving, then it is called as, if both are stationary, then it is called as bistatic. So, in the previous case, that is with pulse radar, The radar transmits a pulse during a very little time, that is 10% of the total time duration. Only 10% of the time duration it transmits a pulse, and rest of the 90% of the time the radar waits for the echo signal. Now, one antenna will be sufficient in the pulse radar case. That antenna which transmits at any point of time, radar antenna have only one task to do. During the first 10% of the total time, total wavelength, it acts as a transmitting antenna. Rest of the time, the same antenna acts as a receiving antenna. Here, in CW radar, a continuous sine wave needs to be transmitted. So, at any point of time, it have only one duty, which is transmitting a continuous sine wave. So, the echo signal, to receive the echo signal, the same antenna cannot be used. So, that is the reason why CW radar have two separate antennas, one for transmission and another one for receiver. So, it have two antennas and it relies on the principle called Doppler shift. Now, this Doppler shift, principle of this Doppler shift is when the target is stationary, the frequency of received signal echo will not have any change. If it is changing, then we can say it, the Doppler effect has came into effect. So the basic concept is if the target approaches the radar, the frequency of the the frequency of the Doppler signal or the Doppler shift will be positive in the case when the target is approaching us. The same Doppler frequency will be negative if the target is going away from us, that is called receding. This happens because consider n wavelengths are there between you and the target. You are the radar, CW radar system. You are at the CW radar system, and between the target and you there are n lambdas. If the target is coming towards us, that n lambda occupies a distance of r. When the target is approaching you, this r is decreasing. That means the time required to execute n lambdas is reduced. When lambdas are reduced, what do you feel? What do you understand? Frequency will increase. If the lambda value increases, what do you understand? The frequency will decrease. So, this concept can be explained with this point. The presence of frequency shift in the received echo signal in the radar due to moving targets is known as Doppler effect. Moving targets causes a frequency shift in the transmitted signal. That is because of Doppler effect. When an observer moves relative to a source, there is an apparent shift in the frequency which is known as Doppler effect or Doppler frequency. If the radar station is stationary and transmitting a same frequency f0, and the observer moves towards the radar station, then the frequency will change. Then the apparent frequency, the frequency that is experienced by the observer, will be changing. That change is because of the Doppler effect. This is the definition of the Doppler effect. When there is a relative motion between the radar and the target, is based on recognizing the target change in the echo signal frequency caused by the Doppler effect. If either the observer or the source is in motion, then it results in a frequency shift. The resultant frequency shift is known as Doppler effect. What we understand by this statement is when there is a relative motion between the target and the radar station, the echo signal will undergo an effect called Doppler effect. Consider if r is the distance from the target to the radar station. The total number of lambdas that occupy between the radar station and the target is, let us say, n lambda. The path length of the electromagnetic signal is it has to start from the transmitter, go to the target, and again come back to the transmitter. So it has to start from here, go to the target, and come back to this distance, that is 2 into r, 2r. Now, how many lambdas are there between in this path? That is 2r by lambda. Because both are in meters, we don't write any units for this total number of wavelengths. Total number of wavelengths is equal to 2r by lambda here. Since one wavelength is called as a phase change of 2 pi radians, one wavelength is representing a phase change of 2 pi radians. So this phi is equal to 2 pi radians, which is equal to again lambda. Now, since the wavelength corresponds to the angular excursion of 2 pi radians, the total angular excursion of phi made by the electromagnetic wave during its transit to and from the target is in radians. Therefore, phi can be written as 2 pi into total number of wavelengths, where the total number of wavelengths are 2r by lambda. So 2 pi into 2r by lambda, which is equal to 4 pi r by lambda radians, is the total number, is equal to phi. Now, the angular velocity or the angular frequency is omega d. Omega d can be written as 2 pi fd, 2 pi fd, which is nothing but d phi by dt, rate of change of phase per unit time, which can be written as 4 pi Vr by lambda because the total number of wavelengths is equal to 4 pi r by lambda. Now this is distance. The rate of change of distance is called as velocity. So 4 pi Vr, it has become d phi by dt. d phi by dt is equal to 4 pi dr by dt into lambda. Then dr by dt can be written as Vr, which is shown here. Vr is equal to dr by dt, and your final Fd will become 2 Vr by lambda, 2 Vr by lambda, where lambda is c by f naught. If you replace lambda with c by f naught in Fd equation, Fd is equal to 2 Vr by lambda. So 2 Vr into by lambda is equal to c by f naught. So if you write this in a proper form, it becomes 2 Vr f naught by c, which is proportional to, which again can be written as Fd is equal to 2 Vr f naught by c, where f naught is the transmitter frequency. Now, by this definition, this is the derivation for the Doppler frequency. So, This is about Doppler frequency. The Doppler frequency Fd is equal to 2Vr by F naught. Now let us understand how the CW radar works basing on Doppler frequency shift. See this diagram, it's a continuous transmitter which is transmitting a frequency F0. This F0 is given to the transmitting antenna. This stronger signal which you can see on the display is incident wave which is stronger and with a frequency of F0. This incident wave goes, hits the target and comes back again. The difference between the incident wave and the target is there are two differences. One is it's in its strength. As we have discussed in the previous lectures, that incident energy will be around 200 watt, 500 watt or 1000 watts even in some cases. So, which is very large, whereas received signal will be of the order of milliwatts or microwatts in some cases. So, that is one difference. Another difference is the transmitted signal has a frequency of F0 and the received signal has a shift of plus or minus Fd, which is because of the Doppler effect. The received signal is F0 plus or minus Fd. This plus or minus Fd has happened because of the movement of the target. If the target is approaching us, this will become plus Fd. If the target is going away from us, then it will become F0 minus Fd. The frequency which is transmitted F0 is also supplied to the mixer. Now this mixer is getting two inputs. One is F0, another one is the received echo, whose frequency is F0 plus or minus Fd. Now this mixer heterodynes both the inputs, and in the resultant this F0 gets cancelled with the F0 in the echo signal, and the resultant is plus or minus Fd, which is nothing but Fd. So after the mixer, the frequency of the circuit has become Fd, which corresponds the relative velocity of the target with respect to the radar system. Now, as we know, always the mixer output can also be called as a bit frequency. So the amplifier following the mixer can also be called as bit frequency amplifier. Now this amplified signal is given to the indicator to display at what velocity the target is moving, whether the target is there or not. If the target is there, at what velocity the target is moving. So this is how a simple CW radar works. I hope you understood the concept. If you have any doubts, you can write into the message box or in the form of a comment. I will be happy to answer your queries. Thank you very much.